This is the second of 3 videos on correlation. In it, we'll discuss calculating and interpreting the correlation coefficient. We ended our last video by introducing the formula for covariance, noting that it reflected the degree to which 2 variables varied together across individuals. If someone's high on one, do they tend to be high on the other? If they're low on one, do they tend to be low on the other? But the problem is that the covariance is in the raw units of whatever x and y are. So it can really take on any value, albeit positive or negative based on the overall direction. We're back to that familiar issue of determining whether some value is large or small, this time with the covariance. It all depends on the scaling of whatever x and y are. In essence, what we need to do is standardize the covariance somehow. We can do this by dividing the covariance by the product of the standard deviation of x and the standard deviation of y. Remember, the covariance is based on the cross products of x and y, so we're dividing by the product of the standard deviations of x and y. We call this the Pearson product moment correlation after Carl Pearson, a mathematician often credited with being the father of modern mathematical statistics, who came up with it in the late 1800s. We'll refer to this as the Pearson R, or just R. In addition to dividing the covariance by the standard deviations, you can also calculate the Pearson R by converting x and y to z-scores, calculating the cross product of these z-scores, and dividing by n-1. The Pearson's product moment correlation, or Pearson's R, is probably the most widely used measure of the association or the correlation between 2 variables. When people talk about correlation, they're usually talking about the Pearson's R. R tells you the direction. Is it a positive or negative association? And how tightly clustered the scores are along that linear or straight line association. But R doesn't work for U-shaped or curvilinear associations because they don't reflect that straight linear pattern. The value of a Pearson correlation, the correlation coefficient, can range from -1 to +1 based on just how negative or how positive the association is. Correlation coefficients can't be less than -1 or greater than +1. But whatever the value of the correlation coefficient, it's important to remember that simply finding some type of association, regardless of the direction or regardless of the strength, does not mean that one variable is in some way causing the other. It's possible that some third variable is in fact causing both. Inferring causation from correlations is a very scary thing that unfortunately happens just about every day with research, and not just on Halloween. One of the most famous examples of this point, that correlation doesn't imply causation, is seen in the correlation between ice cream sales and drowning deaths in California. When ice cream sales are lower, drowning deaths are lower. And when ice cream sales are higher, drowning deaths are higher. Is it possible that ice cream leads to an increased risk for drowning? Maybe your mother was right when she said don't go swimming after eating or you'll get the cramps. Does ice cream have some effect on people that makes them suddenly forget how to swim? Now, of course not. This association is due to a third variable, temperature. When it's warmer, more people eat ice cream and more people go swimming. More people swimming creates more opportunities for people to accidentally drown. When it's colder, people eat less ice cream and swim less too. Fewer swimmers means fewer drowning deaths. This is what's called a spurious correlation, a false association between two variables that's really due to some third variable that influences both. Now, as we said, correlation coefficients can range from +1 to -1. The very largest positive value a correlation can be is +1. A correlation of +1 indicates that all the data falls in a perfectly straight line with a positive slope. It's a perfect positive association. You can think of it as the Mary Poppins of correlations.
As I expected, Mary Poppins practically perfect in every way.
In the opposite direction, the very largest and negative value a correlation can be is -1. A correlation of -1 indicates that all the data falls in a perfectly straight line with a negative slope. It's just as perfect of an association, it just has a negative slope. In between a perfectly positive correlation of 1 and a perfectly negative correlation of -1 is a correlation of 0, which indicates no linear association between the two variables. Whatever the value of one variable has no relationship at all with whatever the value of the other variable is. Visually, you can see this trend from a perfect positive correlation of 1 to no association or a correlation of 0 to a perfect negative correlation of -1. So a correlation of 0 indicates no association. It reflects the smallest correlation. As the value of the correlation coefficient moves away from 0, either in a positive or negative direction, the strength of the association increases up to a perfect correlation of plus or -1. In that sense, it's important to recognize that the strength of the correlation is in the absolute value of the correlation coefficient. A correlation of positive 0.8 is just as strong as a correlation of negative 0.8. And in fact, a correlation of negative 0.6 is stronger than a correlation of positive 0.5. Because it's standardized and can only fall between -1 and +1, once you calculate a correlation coefficient, the natural question is, what constitutes a large correlation? There are a variety of guidelines that people have promoted, but probably the most common are the ones proposed by Jacob Cohen. Cohen suggested that a correlation of 0.5 reflected a large effect, while a correlation of 0.3 a medium-sized effect, and a correlation of 0.1 is only a small effect. Of course, this applies to both positive or negative correlations. A correlation of negative 0.5 is just as large as a correlation of positive 0.5. I gotta be honest with you. I and a lot of statisticians get a little nervous when we start talking about what constitutes a large correlation. In the end, what makes a correlation or any measure of effect, large or small, really depends on the variables being examined, the type of statistical model being used, and the nature of the question that's being posed. As we'll see in a moment, sometimes an effect that looks quite small as a correlation may in other ways be rather large. Now, another way to interpret a correlation is to square the value, calculate r squared, which is sometimes referred to as the coefficient of determination, or just r squared. As you read the literature, you'll often find researchers talking about the squared correlation coefficient, or r squared. They may talk of this as the proportion of the variance in one variable that's related to another. In a loose geek translation, You can essentially think of it as kind of like indicating how much of the variability in one variable you can understand based on what you know from the other variable. For example, let's say we have a sample of children and you have data on their reading ability and nothing else. Here we've graphed their scores along this vertical line from very high to very low. If you were to guess any given child's reading ability, it could be anywhere in that range. This is a situation where we know nothing else about any other data or the relationship between reading ability and any other variables. We don't know anything. We're Sergeant Schultz from Hogan's Heroes.
I see nothing. I know nothing.
But what happens if we know that child reading ability is related to the amount of time parents spend reading to their child? What would it look like if we added the amount of time parents spend reading to their child to the x-axis and created a scatter plot where each of these points is now plotted based on both parent reading time and their child's reading ability? Well, scores would now be plotted along both dimensions, and it may look something like this. Notice that there's now a clear, strong, positive association between the two. Notice how things change once we take into account the correlation between parent reading and child reading. Instead of guessing wildly across the entire range of reading ability scores, if you know how much the parent reads to the child, you have a much better sense of the child's own reading ability. For example, if the parent doesn't read very much to their child, his or her reading ability is probably somewhere in the lower range. On the other hand, if the parent reads a lot to their child, his or her reading ability is probably in the higher range. We're able to make a much more accurate and much more narrow guess because we know something about the correlation between parent reading time and child reading ability. In essence, there was a great deal of variability in child reading scores when we ignored or didn't know about parent reading. However, once we know how much the parent reads to the child, the variability is much less. In other words, researchers can account for a lot of that initial huge variability in child reading by knowing about parent reading. Again, if you're trying to guess a child's reading score and you know how much the parent reads to the child, you don't have to guess wildly across the entire range. You can now guess much more precisely within the narrow range of scores for that level of parent reading. As noted previously, variations of this will often be discussed in terms of the proportion or percentage of the variance accounted for. But to be honest, a lot of researchers really don't understand where this comes from. In that sense, I think this illustration gives you a pretty good idea of what we mean by those terms. However, I have to be honest that this is not exactly correct because variance is a squared value. It's the standard deviation squared. But conceptually, this example helps to understand what we mean by the percentage or proportion of the variance accounted for, and why researchers like to account for variance. It reflects a greater understanding of why we see high or low scores on some outcome, rather than just blindly guessing. So if the correlation in our example was 0.60, the r-squared or coefficient of determination would be zero point 0.6 squared or 0.36, indicating that 36% of the variance in child reading ability is related to the degree to which parents read to their child at home. Again, because we know the correlation between the two variables, if we know parent reading time, we can make better predictions of child reading ability. R-squared is a way of quantifying this effect by telling us the proportion of variance in reading ability that's related to or accounted for by parent reading time. In this case, the proportion of variance we could account for was 0.36, or 36% of the variance in child reading ability. We can also estimate the proportion of the variance in reading ability that is not accounted for or is unrelated to parent reading time. This is just 1 minus r squared, or in this case, 1 minus 0.36 or 0.64. In other words, 64% of the variance in reading ability is still unaccounted for. That wraps up this video. In our final video on covariance and correlation, we'll discuss additional factors that can influence the size of a correlation coefficient. Okay, bye for now.